Restarting. Welcome to Mid-Morning Math with Caitlyn Calculus. We have breaking news today regarding FRQ number 1 Form B from 2007 that has been destroying the hopes and dreams of students for nearly a decade. Our on-site calculus expert Louis L'Hopital has finally solved the three-part problem regarding area. Over to you, Louis.
Greetings, fellow comrades of the calculus domain. As mentioned by the stunning Caitlyn Calculus, I, Louis L'Hopital, am a renowned math guru. The 2007 AP Calculus BC Form B FRQ number 1 has bewildered my brain due to my void of vision. However, my tactile sense has triumphed in comprehending the complicated calculus question. As I rub my palms over the FRQ, the answer and resolution and solution and result are revealed to me. It's a very mind-boggling practice to perfect, but my in-depth hand sensing has allowed me to...
Okay, and on to Part A of Calculus 2007 FRQ number 1.
Hello everyone, and welcome to Part A of our FRQ. So, it says to find the area of R, and up here in this problem it said R is the region bounded by the graph of y equals e up to the 2x minus x squared, and the horizontal line y equals 2. So it's going to be this area right here. Now before we go any further, I think it's smart to type everything into the calculator because we know we're probably going to have to use it at one point because this is a calculator active question. So I have typed my e up to the 2x minus x squared and my y equals 2 into my y equals, and I've graphed it so that the window matches the one shown here, just because it makes everything easier to see. Alright, so now let's get started on the problem. We know that to find the area, we're going to integrate. This is where we run into our first issue because we don't know what the bounds are. We see an intersection here and here. We'll call this A and this one B. We're going to be using our calculator to find these bounds. So what you're going to do is you're going to go to Second Calc, all the way down to intersect. We're going to move the cursor over to where the intersection point is. Alright, and press enter 3 times. 1, 2, 3. Okay, we get x equals 0.4460570. That's not a decimal that we're going to want to deal with in the future, so let's store it into the calculator. Second quit, alpha x, store alpha a. Okay, now we're just going to write that down on our paper so that the AP graders know that that bound didn't just come out of nowhere when we integrate with it. A equals 0.446057021. Now we're going to use the same process to find our bound for B. Go back to the graph, Second Calc, all the way down to intersect, and we will move our cursor over to our second intersection point. There we go. Enter 3 times. B is going to equal 1.553943. Again, we're just going to want to save that so we don't have to deal with it again. Second quit, alpha x, store as alpha b. Alrighty. I'm going to write that bound down again. B equals 1.55394295. And now we're ready to integrate. So it's going to be our integral from A to B, and then it's going to be the curve, so e up to the 2x minus x squared. But we have to pause here because there's something important. If we just finish integrating now, we're going to include this whole area right in here. And we don't want that because we only want the area of R. So in order to remedy that, we're going to subtract 2 from our curve to show that we're subtracting the area of that line. It's important to add the dx because we are integrating. So now all that's left is to type this into our calculator. It's math 9. If you're on a TI-84, it's going to be alpha A to alpha B. I know that I typed my y equals e up to the 2x minus x squared into my y1. So that I don't make a mistake, I'm just going to do this. My vars minus 2 dx. And I'm going to get 0.5141427,856. That's not really a decimal I want to deal with, and we know that on the AP exam you only have to round to 3 decimal places. So my answer is going to be 0.514. And that's all. Let's go to part B with Louis L'Hopital.
That was a real rascal. The area of R required ridiculous rations of reasoning to realize the resolution.
Indeed. A man with a big brain and an even bigger vocabulary. Impressive. On to part B.
Greetings, fellow comrades of the calculus domain. I, Louis L'Hospital, will show you how to solve Part B of FRQ number 1, Form B from 2007.
So as Caitlyn mentioned, Caitlyn Calculus, I already graphed the function, and I put the curve y equals e to 2x minus x squared and y1, the horizontal line y equals 2 and y, and the second part of y equals, and then the horizontal line y equals 1 and y equals as well. And I already preset the window to match that of the graph here. And what we're going to do, we're going to start off, well, part B starts by saying find the area of S. And S is the shaded region between the horizontal line y equals 1, the horizontal line y equals 2, and then the curve y equals e to the 2x minus x squared. So it's this area within here. And then I also stored the intersection points from earlier that Caitlyn found, which are right here, which we'll label as A and B. And those will come in handy later. But right now, I'm going to focus on finding these two new intersection points between the curve and the horizontal line y equals 1. So we can go about doing that by going to second, calc, intersect, and scrolling to where it looks like the horizontal line y equals 1 and the curve intersect. So it's asked for first curve, we go down to the intersection point, we hit enter, and it says second curve. And right now, the cursor is on the horizontal line y equals 2. So we must hit the down arrow to go to the horizontal line y equals 1 to give us our second curve, and then we hit enter again to give us our guess. And what we see here, it's a very small number written in scientific notation. So we're just going to assume, we're not going to assume, we're going to name this intersection point as x equals 0 because it's a very small number, so we're just going to round it to 0. Next, we're going to find this intersection point right here between y equals 1 and the curve. So we're going to do same thing, second calc, intersect, scroll over to where it looks like they intersect, and due to my void of vision, it's very difficult to see these intersection points, but I'm guessing it's somewhere around right here. First curve, we know it's the curve we're on. Same thing as last time. Second curve, you have to hit the down arrow to scroll to move the second curve down and select the line y equals 1 because right now we're on y equals 2. So move down, we're on the correct line now, then hit enter again for our guess. And it says our intersection point is right here at x equals 2. So those are our new intersection points. So I'm going to write, it says find the area of S. I'm going to write that A for area, and I'm going to write subscript S so we know that we're doing S. And as Caitlyn Calculus mentioned in the previous problem, how we find the area, we take the integral to find the area under a curve. So we're going to start by taking the integral, and that's what we're going to write. And first, we're going to put in our two new intersection points from 0 to 2, right here. But when we say 0 to 2, what we're really saying is here's x equals 0 and x equals 2, if we do the vertical lines. But when you just write this integral right here, we're taking the area of everything between those points, which includes the area below the shaded region S and the area of R above it. So the important thing is we need to get rid of those points, or those areas that we don't want. So we're going to start by taking the integral of the original curve, which is e to the 2x minus x squared. And first, to get rid of this bottom red part, because we just want the area of S, we're going to subtract 1. By subtracting 1, that shows that everything below the horizontal line y equals 1 is going to be taken out of the integral. So this red area right here is going to be disregarded while finding the area.
and then we're going to throw a dx on the end of that because we're integrating in terms of x. And now, since we got rid of this bottom part, right now we're just, by using this right here, we have the area of S and the area of R. So in order to find the area of S, which is stated for part B of this part of the FRQ, we need to subtract the area of R. So we're just left with the area of S. So right now, we'll start by taking the integral as written above, just as it's written. So second quit, we'll go to math 9 to pull up the integral. Our bounds are 0 and 2. And as you can see in y1, we already have the equation. So what we're going to do, we're just going to hit second quit. And instead of typing that equation out so I don't mess up, I'm just going to go to vars, y-vars, function, and then put in y1. So that's what this is right here. And I'm going to subtract the 1 which we said, which will eliminate all of this area. Throw the dx on the end of there, and that's going to give us a value of 2.060156,939. And then to subtract the area of r, if you look back at part A for Caitlyn calculus this section, the area of r we found to be 0.514. So we're going to subtract that minus 0.514. And therefore, the area of S, by using this method, we found a solution of 1.546 when we rounded to the thousandth place, which you will do on the AP exam. So that is one method to finding the area of S. Right now, I'll show you a different method.
That was a scandalous scallywag. The area of S stipulated serious sources of sense to showcase the solution.
Your nicknames for these problems are borderline offensive, and I would recommend scaling back if you would like to return to the mid-morning math show in the future.
All right, welcome to part C of our video. Part C reads, write but do not evaluate an integral expression that gives the volume of the solid generated when r is rotated about the horizontal line y equals 1. So we know that generally to find the volume of a solid, its volume equals pi times the integral of r squared dx. But in this case, since we're trying to omit s, it's going to be volume equals pi times the integral of big R squared minus little r squared. So we're going to start this off by figuring out what our big R and our little r are. So our big R is going to be from the top of the curve all the way down to the x-axis. So let's start off by writing that. We know that again that our bounds are going to be from A to B. And I rewrote those for you guys. Okay, and so our big R is from the top of the curve, e to the 2x minus x squared, and then all the way to the x-axis. But what we have to remember is that we're rotating around the horizontal line y equals 1, which means that we have to subtract 1 from this part of our big R because we don't want to include the area that's down here. All right, and we always have to remember to square it. Okay, and now we have to separate out our little r, which is going to be right here because that's the area that we don't want included in our integral. So that's going to be from 2 to 1 squared dx. All right, so what we've done here is we've taken out the s and we've taken out the area between y equals 1 and the x-axis, and this is what our integral is going to look like. Now that's going to be the answer because we don't have to evaluate it, so that's going to be all for part C. Now let's go back to closing remarks with Louis L'Hopital.
That was a vivacious villain. The volume of the solid violated various veins of the knowledge to vindicate the resolution.
All right, sir, I've had quite enough of you. From here on out, you are banned from the mid-morning math show. I hope this program has successfully taught you how to solve FRQ number 1 from Form B from 2007. After all, this is a pass or fail situation. It's so dumb.